Finally, covalent bonds. Okay, covalent bonds form when atoms are forced to share electrons. And when they share electrons, they go in pairs. So one bond, one covalent bond, equals 2 shared electrons. Now, in order for us to make molecules using covalent bonds, it's helpful to keep track of the electrons using Lewis dot structures. And these are simply the chemical symbols off the periodic table surrounded by dots, where each dot is a valence electron. We talked about valence electrons in an earlier video. They're simply those electrons in that outermost shell. The outermost shell. They're the ones on the surface of the atoms, the valence electrons. And what's handy is knowing how many valence electrons for each element. So simply go to the top of each column of the periodic table, ignore the little a, and you got them. Those are the valence number of electrons for each family of elements in that column. Okay, and it's still true. All the elements want to be like noble gases and have their outermost shell filled. How many electrons does it take to fill the outermost shell? 8. Those are the valence electrons. And so all the other elements want to get the 8 valence electrons. What that means is each atom wants 8 dots. Oh, and there's always an exception in every rule, right? Helium only has 2 dots, 2 valence electrons. That's what hydrogen wants. It wants 2 dots too. Then its outermost shell will be filled. We can make a prediction as to how many covalent bonds it should have. It usually equals the number of electrons the atom wants to gain or lose. Let's look at hydrogen gas. You have 2 hydrogen atoms, right? That's what the formula says. Hydrogen, well, it's not part of the alkali metal family, but it is in the same column. There's 1 valence electron. And that makes sense. It has 1 proton. It's going to start out with 1 electron to balance the charge. So in the Lewis dot structure, each valence electron equals 1 dot. And what's handy is to put single dots facing the other element. So I'm going to put the 1 dot around the hydrogen, and then the second hydrogen, I'm going to put its 1 dot, 1 valence electron, on the left, so that this dot faces that one. And then you kind of squeeze these together so that they pair up. The 2 electrons are in between the 2 hydrogens. They're paired up, and hey, each hydrogen thinks it has 2 electrons. They're sharing 2. So this hydrogen sees 2 dots, and this hydrogen sees 2 dots. They both see 2 dots. They both think they have the same number of electrons as helium, and that makes them stable. We got a stable compound, hydrogen gas. Let's try carbon dioxide. Okay, carbon, it's in column 4A. It's got 4 dots. And then when you draw Lewis dot structures, you should spread out the electrons, right? They're electrons, they're negative, they repel each other. So spread them out. And the legal places where you can put them is up, down, left, right. It's not going to always be useful, but let's try putting the atoms along a diagonal. And now, oxygen, how many valence electrons does it have? 6. 6A. So put them top, bottom, right, left. We spread them out, but that's only 4 dots. Oxygen comes in with 6 valence electrons. Okay, so the trick is, when facing the other element, keep them unpaired. And then after you've used the 4 locations, top, bottom, left, right, you have to start pairing up the electrons. So oxygen has 6 valence electrons. I just gave it its 5th electron, and now here comes the 6th one. And I set these pairs of electrons away from the atom it wants to share electrons with. Sort of like oxygen's being greedy. It says, hey, I don't want to share these pairs of electrons, they're mine. But maybe I'll share this 1 electron here and this 1 electron here. Let's do the same thing with the other oxygen. Starts out with 6 valence electrons, spread them out, first 4. Time to pair up the last 2. I'm pairing up away from the element, the carbon atom. Okay, now you want to just squeeze these together so that these 2 electrons pair up, these electrons pair up, these 2 electrons pair up, and these 2 electrons pair up. And there's a Lewis dot structure. And since 2 dots equals 1 line, 1 covalent bond has 2 shared electrons, you can decide to pair up your electrons and just draw lines, or you can keep them separate. But if you draw lines, it's easier to see that they're covalent bonds. Ooh, let's use that trick, that one guideline. The number of covalent bonds usually equals the number of electrons an atom wants to gain or lose. So how many electrons does carbon want to gain or lose? Well, it's a non-metal. It's on the right side. It wants to gain. So it wants to go from 6 electrons up to 10. Yikes, that's 4 more electrons. That's tough to do. So instead of trying to gain 4 electrons and become an anion, it says, nope, I need to share electrons. And it ends up making 4 bonds because it wants 4 electrons. So carbon, 4 bonds. Oxygen, it wants to gain 2 electrons. Since it wants to gain 2, it tends to make 2 bonds. And if you think about these nonmetals gaining electrons, they both want to gain. Neither one's willing to lose. Well, that's what kind of forces them to share and become covalent compounds. One last example. Let's do nitrogen gas. It's in column 5A, so 5 valence electrons. So 1, 2, 3, 4, and then pair up away from the other element. So now this nitrogen has 5 dots, 5 valence electrons. Do the same thing on the second one. Pair up the 5th electron away from the other atom. And now make them share. These 2 atoms pair up to form a bond. These 2 pair up to form a bond. These 2 pair up to form a bond. Hey, that's a triple bond. Carbon and oxygen is making a double bond. We could draw the Lewis dot structure of hydrogen gas and show a single bond. Okay, let's finish off here. When you name covalent compounds, you have to use prefixes. And that's because there are sometimes more than one way to connect molecules together with different numbers of atoms. Second thing, ionic compounds are the ones that separate when they dissolve in water. Covalent compounds usually stay together. So here's sucrose or table sugar. Carbon, hydrogen, oxygen are all nonmetals. So the atoms are stuck together through covalent bonds. So when it dissolves, it's still intact. So stir up some crystals of sugar and you see it all, the little particles disappear. Well, this big long chunk can be thought of as a crystal of sugar. And as it dissolves, individual molecules, each one with this chemical formula, C12H22O11, breaks off of the crystal and swims around the water as dissolved sugar. Okay, that's all for now.